I'm Léonie Buckley. Along with Emily Dunkel, we'll be presenting benchmarking deep learning on the Myriad X processor on board the ISS. Future space missions will need more powerful onboard computing to meet mission and science objectives. The time delay between Earth and space systems can be prohibitive to mission goals. Deep learning is state of the art when it comes to computer vision and artificial intelligence. However, power limitations and harsh space environments make the deployment a difficult task. Taking these challenges into account, our goal is to demonstrate and benchmark various models running on the Myriad X onboard Hewlett-Packard Enterprise's spaceborne Computer 2 payload on board the ISS. And here we have our team. We include members from Ubotica, the Jet Propulsion Laboratory from the California Institute of Technology, and Hewlett-Packard Enterprise. To begin our talk, I will discuss the Myriad X and demonstrate how to port models to the processor. Emily will then deliver an overview of the experiments conducted and I'll provide the results obtained. Emily will then give an overview of prior flights which have deployed machine learning inference on board. We'll discuss future working conclusions and finally provide references. In this slide, I'll provide an overview of the Myriad X processor which has been developed by Intel Movidius. The Myriad X provides 16 very long instruction word vector cores, called shaves. Also provided are two neural network processing units called Neural Compute Engines, or NCEs, as well as various dedicated imaging and vision hardware accelerators. The operating system is managed by two RISC-Leon processors, which manage the processing of input and output data to the host machine. This hardware configuration and the use of parallelization allows for performance of up to 4 trillion operations per second, 1 trillion of which are dedicated for neural network compute. The software package for the Myriad X is highly configurable, providing a complete hardware software package. The low power budget of around 1.5 watts, along with the low thermal budget, makes the Myriad X suitable for in-orbit applications, which has been demonstrated in other projects. The previous generation Myriad, the Myriad 2, flew on ESA's VSAT mission. Inference models, trained using a variety of programs, can be ported to the Myriad X using the conversion flow displayed in this slide. Caffe, TensorFlow and ONNX models are some of the supported model types. Using the conversion flow is software provided in the OpenVINO toolkit, which is an open source toolkit for optimizing and deploying AI inference and is developed by Intel. In this example, the starting point for the model is a PyTorch model, which requires a conversion to an ONNX model using a script provided in the OpenVINO toolkit. Next, the ONNX model is converted to an intermediate representation using the OpenVINO Model Optimizer tool, from which the Myriad compatible tool is compiled. This compile tool allows the compilation of models compatible with any available Intel hardware such as CPUs and GPUs or Myriad VPUs. This compiled.unn model format contains the weight and topology of the network in floating point 16 format. These tools allow for various values to be baked into the model, such as scale and mean values. The hardware resources to be allocated to the model on the Myriad X may also be specified. Communication is provided from the host machine to the Myriad X over either USB or Ethernet, over which the models are deployed to the Myriad X using the Ubotica CVAI toolkit.
I'm Emily Dunkel, and I am going to go into more detail on the ISS experiment. HPE's Spaceborne Computer 2 was delivered to the ISS in February of 2021 and powered on that May. 2 Intel Myriad X VPUs have been delivered and integrated with SBC2, and a set of deep learning algorithms have been run on board on the ISS. And we're going to talk more about that in this presentation. In addition, 2 Qualcomm Snapdragons have also been delivered and integrated with SBC2. If you're interested in that work, please see the presentation by Jason Swoop. This work was sponsored by the Earth Science Technology Office. Here is our experiment setup. We develop and test locally, and once that's working, we test on Hewlett-Packard Enterprise's ground testbed. Next, we give our test harness that runs all our models to HPE. They test on their ground testbed before deploying it on board the ISS. Then HPE sends the results back to JPL, and we compare with what's expected. I'm going to talk about some of the JPL machine learning models. Léonie is going to give the results, as well as talk about some Ubotica models. I'll discuss 3 Mars classifiers, as well as a pixel-wise Earth-based classifier for flood mapping. Léonie will discuss ship segmentation and a DDR memory test, which can give us an idea of radiation effects. And this is really to show a range of the models that can be deployed on the Myriad X. The first model that we ported to the Myriad X classifier is deep learning for landmark classification. On the right, I show some example images, and these were collected by the HIRISE instrument on board the Mars Reconnaissance Orbiter. The model does Mars surface feature classification using this imagery. You can see some of the classes include things like dunes, craters, and impact ejecta, as well as things that come about due to sublimating CO2, such as spiders and Swiss cheese. So those really interesting features on Mars. If this model was running on board MRO, it could be used for things like autonomous data collection, targeted downloads, so only downloading classes of images we're interested in, commanding space assets like the Mars rover, or science interpretation. If you know a bit about deep learning models, this model was built using transfer learning from AlexNet. AlexNet was trained on Earth imagery, really internet imagery of things like dogs and cats, and then the model weights were fine-tuned using this Mars imagery, which is quite different from Earth-based imagery on the internet. The next model we ported also deals with Mars imagery, but this one is not collected by an orbiter, it's collected by the Curiosity rover. So it uses data from the MASS camera and Mars Hands Lens imager on board the rover. Some examples of those images are on the right. There's a drill hole and sun. And some applications for this could be onboard navigation or onboard science interpretation. Like the previous model, this model was also built using transfer learning from AlexNet. If this model predicts the class other rover parts, it is then passed into the next model I'm going to talk about. Some examples of the images this classifier classifies are things like observation tray or the rear rover deck. So applications of this could be for spacecraft health analysis.
The models described by Emily were all compiled for, run, and benchmarked on the Myriad X. The first step in the benchmarking is to examine the absolute number of classification errors when the outputs of the model on the Myriad are compared with those obtained on a PC. The highest number of classification errors found was 3, with a percentage discrepancy of 0.5%. When the results obtained in flight were compared with those obtained on Earth, no bit errors were recorded. The average inference time was also determined, with each model recording an average time of around 16 milliseconds per image, which equates to between 61 and 62 frames per second. This is favourable when compared with running the same models on the PC, which recorded a time of 56.9 milliseconds or 17.5 frames per second.
So now we're going to go back to Earth and look at deep learning for flood mapping. The previous models I talked about all did classification of an image. So given an image, what class of objects is it? In contrast, this model does pixel-wise classification of the images and is basically classifying them as flooded or not flooded. It uses UAVSAR imagery, and it's been trained on data from Hurricane Harvey. So some applications here could be for flood mapping, or alert generation. If you're familiar with machine learning models, this uses a Unit 6 architecture, which is a fully convolutional model and has a contraction and expansion path.
The UAVSAR model was also ported to the Myriad X, using the same method previously described. Again, the quantization discrepancy was recorded at the development phase, as well as the inference time. The images at the bottom of the slide demonstrate how the visual output of the model run on the Myriad X matches that from the model being run on a Linux PC. The throughput on the Myriad X was found to be 166 frames per second, which is much faster than the 25 frames per second that was achieved on a Linux PC. The final network benchmark on the Myriad X is a ship segmentation model, which is used to detect ships from satellite images. Applications include detecting ship traffic congestion, illegal fishing, and piracy. The network was trained using data from an Airbus ship detection dataset from a Kaggle challenge, and the architecture is based on UNet and a MobileNet v2 backbone. It was found that a throughput of 10.2 frames per second could be achieved with images of size 320 by 320 pixels. The final test deployed to the Myriad X on the ISS is not an inference test but a memory test, which specifically tests the half-gig DDR on board the Myriad X. This test ensures that no sections of the memory have become corrupted and might provide incorrect inference results. 3 tests have been developed to provide full coverage not only of the entire address space, but to ensure that the direction of any bit errors can be determined. The first test involves writing an address's own address value to that address. The second address writes the XORed value of an address to that address. This means that all the bits are flipped when compared with the first test. The third test provides more detailed information. Again, the entire DDR memory space is written to, but this test writes and checks each address 64 times, with a different value being written each round. The first round begins with writing all zeros to an address. Once an address has been checked, the least significant bit is changed to a 1, with each round resulting in the next least significant bit being flipped to a 1. This process is repeated until the address contains all 1s. This begins the process of flipping all the bits back to zeros, beginning this time with the most significant bit, continuing until all the bits once again have a value of 0. This test helps to establish possible errors in addresses where the address may not maintain its value, and any errors that may occur when flipping a bit from 0 to 1, but not from a 1 to 0. No in-flight errors have been recorded in this test thus far.
This work is a continuation of prior machine learning inference done on board. Some examples are the autonomous Spacecraft experiment that did onboard image analysis for intelligent downlink and autonomous retargeting, and the IPEX CubeSat mission. Both of these experiments used non-deep learning models. FISAT-1 was a CubeSat mission from ESA, and it flew the Myriad 2, which is a previous generation VPU, and used deep learning to do automatic discard of cloudy imagery. We are continually benchmarking new deep learning models on the Myriad X processor on SBC2 on board the ISS. Some upcoming models include volcano eruption detection, as well as viable road classification for disaster relief. We have demonstrated fast and accurate inference with the Myriad X. And this is really a step towards a new era of more complex and powerful processing with edge computing. Here we show some references for the Intel Myriad X processor, HPE's SBC2, as well as machine learning references from the models discussed in this presentation. Thank you very much for listening.